the topics are due tomorrow, and I'm happy to answer any questions you have about those. Just go ahead and pop in. Um, you do have a quiz over the weekend over stuff we have covered, and I'll let you know by the end of class whether we need to extend the expert TA another couple days or not. Any questions before we get started? Oh, okay, okay.
Just,
Oh yeah, take your time.
yeah, it's just the homework page, like, because everything just shifted by like a week, so like homework chunk is also due tomorrow too.
Oh, interesting. Wow, I wonder what I was doing that I didn't get that right. Because yeah, it's actually that's not going to be due until November. Okay, I will keep try to keep an eye on that. Thank you though. Any other issues we should speak of? Oh, you guys pretty happy?
I recently changed
Oh,
my
okay,
structure.
so
Is that fine?
that brings us to today's lecture, which is going to start on applications of this whole magnetic force, which I think we discussed mass spectrometers last time. Um, where the cool thing about a mass spectrometer was that you could excite it by shining a light on it or something, and mass spectrometer. And what a mass spectrometer would was analyze something's base particles like molecules or atoms and be able to tell you what they were made of just based on their mass, which is very cool. And so let's talk about how you might build yourself a mass spectrometer where we have this idea of a cyclotron radius. Where something's, where if you put some particle that's electrically charged through a magnetic field moving with some speed, it will go in a circle. Where the faster it goes, the bigger the circle is. The more massive it is, the bigger the circle is. And but also the stronger the charge or the stronger the magnetic field it is in, um, will make it actually go in a smaller circle. So let's say that I made a magnetic field in a region. So like I probably have a vacuum tube here that I have vacuumed out, and I've put in a magnetic field that for this example is going into the page in the negative z direction. Now, if I run a proton into this field, what's which way is it going to go? So I have the speed, the velocity moving in the positive x direction. I got the B field in the negative z direction. So I'm going to get a y. So I'll have a V, V, a B, and a force. Yeah. Everyone, velocity, field, force. Yeah. So it's going to experience a force up, which means it's going to start curving up and go in a circle. And of course, once it hits this spot, you can do the same thing where you're like, okay, V now force is in the negative x direction, right? And so we get this characteristic circle that we talked about last time. Except as it's circling around, it leaves the field right there. So after this, it'll just shoot out that way. Make sense? Where its radius of this circle, pretend I drew a semicircle, is given by that equation. Okay. Okay, start. What if I had shot an electron in here? What would be different? Okay, yeah, so it would experience a force in the opposite direction. If I sent it in at the same speed, so I have the same v there, would it go in a circle, an identical but opposite direction circle, or would the circle be in a different size? What's different about an electron and a proton besides the sign of its charge? Its mass. Where an electron is much, much smaller than a proton, right? So even though it'll have the same magnitude of charge, it's going through the same magnetic field, it's going at the same speed, its mass is so much smaller than its radius is going to be so much smaller. So not only is it going to go in the opposite direction, it's going to have a small little circle there. Okay, so already you're kind of seeing the effects of if I shoot in different types of particles, I'm going to get different answers out. But I said this was a mass selector, not a charge selector. So let's stick to positive particles for a while. So there's a proton. What if I had a gold ion of a +1 charge? So an ion is just like a gold atom that I've taken an electron off. So 1 electron down on my atom. So it's got a +1 charge. So is it going to follow the path of the proton or the path of the electron? First off, it's going to go up or down. Up. And I shouldn't have really said follow the path. Is it going to have the same radius of a proton, this gold ion? No. Is it going to be smaller or larger? Much, much larger, right? So my gold ion is going to go in here, and gold is very big. It's quite a heavy particle. That's why they call it a heavy metal. It would land on like way high up there. So just based on its mass, so it has the same charge, same speed, going through the same field, just based on its mass, I can differentiate what type of particle I have. Because I know a proton and all protons, because protons are all the same, will come out right there. I know gold will come out way up there, lead ions, I don't know what else, arsenic ions maybe, other types of ions would line up where the heavier they are, the further up that wall they would be. And so if I wanted to make a beam of just protons, what I would do is I would just start shooting charged particles into my magnetic field, and then I'd make a hefty concrete wall where I didn't want to see the particles, and I'd make a little hole in the wall just for things with the mass of a proton. And that way I'd only get protons out. I wouldn't get helium ions or gold ions or anything else. I just get protons. If I want gold ions, I'd put the hole, way higher up. But you can put the hole wherever you want, and that will tell you, and you judge that based on the mass of the thing going out. Does that make sense? And so that's a mass spectrometer. Everyone kind of happy with that? Now, you might say, but Dr. Jennings, for that to work, you'd have to have the same speeds. You'd have to have everything going in there at the same speed. And let's talk about how you might get that to happen, because that's a really interesting kind of device, a velocity selector, where you indeed might only want particles with a very specific velocity. And this might be difficult because you might be like heating a filament and it'll spew off all sorts of things. It might not just spew off specific ions of +1. You might have +2, +3 ions. You could have a bunch of different things. And this might be a problem because a lot of times when you're making a particle beam, you need it to have a very specific momentum. You need to have it have a very specific energy. Beyond just science or engineering, there's a lot of material stuff that you can do. There's a lot of medical applications where if you want to try to irradiate a tumor inside someone's body, you need to make sure you have your particle beam set that will go directly to that tumor and then stop. You don't want to shoot a hole through somebody's body. You want to just irradiate one particular part. And so it's really important then that you don't have this beam with really high energy particles and really low energy particles. You need a really uniform sort of beam. And that's where this velocity selector comes in. Where? Velocity selectors are really cool. Where you set up both an electric and a magnetic field. So I have a region in here where I've made an electric field like this. And I'm also going to make a magnetic field going into the board. And I am going to shoot positively charged particles in the +y direction. There's X, there's Y, there's Z. And I want to pick out only specific velocities. So let's go through these effects. First off, my electric field. I have a positively charged particle in an electric field. It's going to experience an electric force. What direction will the electric force be in? Yes, your positive particles want to go along the field, right? So you'll experience an electric force that way, where the electric force is equal to QE. Okay. It's also going to experience a magnetic force because it's a charged particle with some velocity in a magnetic field. Which way is the magnetic force going to be in? Perfect. Excellent job. In the opposite direction, where this is QV cross B. But as long as I have correctly set up my velocity be perpendicular to my field, the angle between them is 90, sine of 90 is 1, and I can just simplify this down to QVB. Sound okay? All right. Now, the goal behind this is I'm going to set up my concrete walls to absorb everything except particles that go straight through. Okay? So right now I have these two forces, they're pushing in opposite directions. If the electric force is stronger than the magnetic force, this thing will go that way. If my magnetic force is stronger than my electric force, it'll go that way. It will only go straight if the net force, which is the electric plus the magnetic, add up to 0. If they're balanced, in other words. So far, so good. Okay, let's look at this. So if I need my electric plus my magnetic to add up to 0. My electric, you have going in the plus x direction, QE. My magnetic, you have going in the minus x direction. So we'll do QVB. I don't really need that anymore. And these need to add up to 0. Okay. What's happening to the Qs, the charge on my particles? They're canceling out. So let me ask you a question. If I had, instead of shooting a positive particle in here, I'd shot a negative particle in here, would it have mattered? I like the no's. Because if I had done that, what would happen is my electric force would be then have flipped, but so would my magnetic force, since they're both multiplied by this negative sign. And so, yeah, they would be pointing in different directions, but they'd still be pointing in opposite directions. Okay. And since this is a velocity selector, what we're really solving for is this V, where you notice if the electric force is equal to the magnetic force, then our speeds are going to equal the electric field divided by the magnetic field. So what you do is you set your electric and magnetic field such that to the velocity that you want, right? Because if you're going too fast after that, your magnetic field will be larger, because your magnetic field depends on how fast you're going. And that takes you along that path. If you're too slow, your electric field will be larger, and that's going to take you along that path. But since your magnetic magnetic force depends on speed and your electric force does not, that allows you that freedom of that one particular variable. Make sense? And so that way you get your one particular speed that'll get you through your concrete walls. Sound okay? Okay. And frankly, a lot of times you use these two things in tandem. So you set up so you have whatever source you have, which usually is a filament that you heat up so it's spewing off stuff. You set up your velocity selector to pick out the right velocity. You put a mass spectrometer right after that. So you then, like, once you have them all going at the same speed, you run it through your mass spectrometer. And whatever you get out is something that's going at the right speed with the right mass. Which, if you think about something like kinetic energy, that's enough to give you a very uniformly energetic sort of being. Sound okay? Okay. So those are like two applications of magnetic force that people use a lot. There's a third that I want to talk about because it's an extremely common thing to see. If any one of you guys goes and works in materials, it's a really, you'll build like a lot of these. which is called a Hall probe. And so the reason that what makes a Hall probe interesting is it allows you to figure out what type of current you have. And so we talked about different types of current a long time ago. And so we kind of had this idea of current that we are going to deal with, where I have my like protons and they just stick, they don't move around. And I have my electrons and they do move around like that, where we would consider this to have a current going in that direction. And we said we had the current going in that direction because electrically, you really can't tell the difference between a positive charge going one way and a negative charge going the other. And we said it didn't really matter. And sometimes it doesn't, and sometimes it does actually. Because where you actually see positive charges, so like positive charges moving, is in semiconductors. Where semiconductors are crystals. I don't know if I need to add a except in this special case, because I think it's pretty uniformly semiconductors are crystals. Where what you do with a semiconductor is you dope it, which means that you add or take away charge. So like for this one, we have, if you notice, I have one positive charge without a negative charge. So it's been doped, so I've got that negative charge out. And what will happen is that with proper application of voltage, where we're going to have like a plus voltage over here and we're going to hook this to ground over here, it will be possible for one of these negative charges to jump off of its proton that it's holding onto. I don't know if you know about crystal, if you've taken your chemistry class yet, but with crystal bonds, their electrons are pretty tightly held to their protons. They're not metal soup. They're not electron soup like metals. They're held on. And so for a charge to jump like that, it's kind of a big deal. But like I say, if you apply your voltages right and dope this right, you can get this effect where you get those charges that bounce from one to the other. And in fact, what it will look like and matter like is this positive pole going in one direction. And so this is something that we would consider a positive charge moving like that. Now notice electrically, we really can't tell the difference on this one. Electrically, we're gonna get the same thing. But very, very often you want to know exactly what is carrying your current. And so we kind of talked about this way back in the day when we talked about like drift velocity and what a current's made out of. We said you take the charge of one carrier and multiply it by however many carriers you have. So this is what we mean by carriers. Like, do you have an electron or do you have this hole in your semiconductor? And depending on how you treat your semiconductor, the charge that you have moving around you might have more or less charge, and it's going to be really important to be able to characterize that, because this is what you're going to build your new computer chip out of. Sound okay? Okay, and so what the Hall effect does is it allows you to see what's carrying your charge. So a Hall probe is what you build to figure out what your charge carriers are. And let's talk about how that would look. So I make a circuit. I've got a battery, I've got a wire, I hook it up to a chunk of silicon. That I have doped in a way that I am curious to see what happens. So I got this mystery material that I'm not quite sure how it's going to work. Now, I know that since there's a positive end of my battery and there's a negative end, current, as defined by where the positive charges are going, is going to go around like that, right? And I know that I'll have some, whatever voltage here is, I'm going to have that voltage here. That'll be 0, that'll be 0. So I have this electric field going down like this through here, where that's where my current's going to be going. But I don't know what's carrying my current. So on top of that, I'm going to throw a magnetic field, B. And so let me ask you a question. I've got too many colors in here now, so I'm gonna reuse yellow. If I have positive charges going down, I have my magnetic field into the board. Which way will the magnetic force be? To the right. Okay, so if I have positive charges floating down through here, some of these charges are going to start build up on that side. Okay, exact same set of circumstances, but I'm about to ask you about negative charges. So my field like that. Okay, now what if instead of positive charges going one way, I really had negative charges going the other way? Which way are they going to feel a force? All right, so it's going to feel a force in the same direction. So I still have the velocity up, force field into the board, my force is that way, but as you said, it's negative, so it flips at the end. So I'm still going to feel a force this way, which means my charges are going to collect on that side, but now instead of being positive charges, they're negative charges. And so here's something we can measure. We can hook up our voltmeter to the thing, and it can tell us whether we have a positive voltage or we have a negative voltage. And in that way, we'll be able to say what our type of charge carriers are. Now you can go further than this, and you can by figuring out how large this voltage is versus how large the magnetic field you put across here is. You can say like what is the charge per carrier. You can say how many carriers you have, so you can more closely characterize this. But that's the basic idea, where different types of charge are going to react to this magnetic field differently. Sound okay? Okay. So that's the Hall effect. Where this thing right here, this is a Hall probe. One day you might build it. Okay. Now, is everyone pretty happy with just like the basics of how magnetic force works? We have I see all the good right-hand rules out there. You guys seem to be doing good on this. Okay. Then let's move on to the next thing, which is now we'd like to, instead of looking at magnetic force per charge, we'd like to look at magnetic force of a current. So what happens if you have a bunch of charges all together? And I don't think you're going to be too surprised. So on a current carrying conductor. Okay. Okay, so we have this idea that if I have a single charge moving in a magnetic field, B, we could say what magnetic force it has. Where here, I'm hoping that you'd see it has a magnetic force in that direction. Sounds good? Okay, and if I have more charges, they will all experience this magnetic force. And maybe I'd like to stop talking about the force per charge, and I'd like to get just some like net effect, which I would do by trying to write this down in some way in terms of a current. So let's get to the current, where we need to start here, because that's really the only place we have to start from. And we need to think of current. So equations we have for current, we have like change of charge over change of time. And let's see if we can do something with that, because we're definitely going to have like a V in there as well if we need to connect these things. So looking at that V, if I have a charged particle going with some velocity, one thing I could say is that velocity is however far it goes, some length, divided by some unit time. Sound okay? And so this magnetic force, QV cross B, I could substitute in L over delta T for my V. Is that okay so far? And you might, one thing you might be looking at here is that I put a little vector on top of my length. And so this is going to be a key thing here. We're attaching our direction to the direction of the wire. If you recall, few chapters back, we said that current is a scalar. It can go forward on the wire, it can go backwards on the wire, but it is constrained to the wire. So when we need to take a cross product, we're going to need two vectors. Our vectors are going to be that magnetic field plus the direction of the wire. So I can have a wire and I can bend it left. And so I can make it a vector because it can turn left. My current will just be a magnitude. It'll be going forwards or it will be going backwards. Sound okay? Okay. That will be kind of a pointless thing to care about because our current is always going to be in the same direction as the length of wire we have. But it's a thing nonetheless. So definitely keep that in your head. Notice that I have now taken that delta T off and I put it underneath my charge, because clearly I want to charge over time. I just got myself a charge over time, and that's going to be current. So I have what I wanted. I have my magnetic force equals current multiplied by this cross product of the length of wire across the magnetic field it's in. Okay, let me circle that. First off, everyone kind of happy with that. Okay. There's a few problems in your homework that'll take you through a right-hand rule on this. One thing just to note is that the current's always in the direction that positive charges would go. So you're doing the same kind of V cross V sort of thing you do, except you're doing the direction of the wire across V, and your current's always considered positive, so you never need to worry about flipping your hand at the last moment. Sound okay? So yeah, so you just do it the same way we did all those right-hand rules on Tuesday. I'm about to dive into some math here. Because one thing you might think is wires don't tend to be that nice. You've been dealing with wires in labs for a few weeks now. They tend to go all over the place, right? They're not always pretty. And so what if you have a wire that's not always pretty in a magnetic field? So if I have a current like this and a magnetic field going like this, sometime my wire might be perpendicular to this field, sometimes it might not. So how are we going to do this? Clearly, we're going to split the wires into small chunks. So let's chunk this wire up. So like I have chunk of wire there, DL, next chunk of wire, DL, next chunk of wire, DL. I can look at any of these chunks of wires and get the angle between my wire and the magnetic field theta, magnetic field. The theta might change. So I would need to take each little chunk, figure out the force of that one little chunk, then add it to the next little force and to the next little force until I have a total force of this thing. My current, as I'm going from different little chunks, should I expect it to be the same or should I expect it to change? I like the same, right? Because it's all these little chunks are in series, right? So we'll put the I outside of my wire, and I have my DL cross B inside of my wire. From wherever you want to start to wherever you want to end. So far, so good? Okay. Let's do a hard but illuminating problem, where I want to look at a closed loop of wire like this, that's in a magnetic field, and I have a current going around counterclockwise. So I have current, and I would like to find the magnetic force on this whole loop of wire. So far, so good? Okay. We're going to do this in two parts. We're going to do the straight line, which will be pretty easy, and then we're going to do the semicircle part, which will be very interesting. I will also give you that we know the radius of this half circle that we're dealing with. So we need this, so we have the current going through this wire, we have the radius of this half circle, and we have the magnetic field. So that's what I expect my answer to be in terms of. Okay, straight line, straight wire first. So I have a straight wire like this. It's got current that way. It's got a magnetic field that way. Do I need to write this down in terms of an integral, or can I just use this equation? I can use this equation, good, because the angle between my current and my magnetic field isn't going to change. Okay, ILB cross force. L cross B. Okay. What is the angle between L and B in this case? Where the direction of L is going to be in the same direction as I. Say again? So L cross B, what direction am I going to get? Right hand rule, right? Yeah. O. So the first part of the right hand rule, L. Second, B. Out of the page. So like we're doing the same right hand rule as before. We're just, instead of V, you say L. But yeah, excellent. So in the plus Z direction. And the angle between these two things is 90. What's the sign of 90? 1. Okay, looking good so far. The only thing that's a problem here is this L. We need it in terms of I, R, or B. Can we relate L to R? To R, right? Since L is the diameter of that semicircle. Does that make sense? So we can say L equals 2R. And so the magnetic force, I'm going to call it, say, on the bottom of this thing, is I 2RB in the plus Z direction. Okay, everyone solid on that? Then we're going to do the hard part now. So the hard part, we have this semicircle. Sorry, my notes are really messed up for this chapter. I'm like scrolling up and down here. Almost there. There we go. I have this semicircle. Oof, like this. Current's going that way. Magnetic field's going this way. So first off, do I have to do an integral on this one, or can I do like the bulk thing like we did on the straight line? I got to do the integral. Okay. We'll put it up here. I dl cross b. Okay. Let me ask you, do y'all have any intuition on what the answer might be? Okay, okay. It'll be a fun surprise then. Okay, so let's start off by drawing a DL. So like I choose a point, I draw a DL here. it's and I'm going to just start drawing everything I know about it. So if I have this DL, it's a distance r away from the center. I'm on a semicircle. So if I asked you like where that spot is, what might be a good answer? Okay, so like it's one radius away from the center, but how do you tell if I chose that side or like that side? Did you say angle? Because I'm really hoping someone's going to say angle here.
Angle.
Angle, awesome. Where it's really easy to identify this by just saying, hey, I'm at this angle right there. Okay, good. And so I'm gonna keep kind of going here. Where my DL, it's that long. I can also say I have this angle d theta there that tells me like how wide my DL is. I do need to figure out the angle between DL and B. So my DL is going out that way. My B is going this way. So I need to figure out this angle here because I'm about to take the cross product between these two. And I'd like to relate it back to this angle theta that I have down here because that would make my life easy. So let's just take a few easy guesses. So like down here at this spot, my angle is 0, right? Theta is 0. What's the angle between this DL right there and B? No answer. So if my DL is pointed this way and my B is pointed this way, what's the angle between those two vectors? 0. Okay, so when theta is 0, the angle between my vectors is 0. Okay, what about if I chose this DL up here, like that, where my angle would be, where theta would be 90, right? What's the angle between DL and my magnetic field there? 90? So we could, and I'll be happy to if you want. We can prove that the angle between my DL and my magnetic field is the same as this angle theta. Or you can just say, okay, well, we've stuck a few angles in there and it seems to work. I have like one person comfortable with this and a few people looking very uncomfortable with it. Should we look at it some more, or do you guys feel satisfied? Okay, I'm sorry, guys. You guys either need to like say you believe it, or you're going to be in for a whole lot of math here. Okay, I'm trying to figure out if this angle right there is the same as this angle right here. Okay. Excellent. And can we say that? I did do this right? This plus this equal 90, theta plus phi equal 90. Excellent. This is 90 because I said one's radial and one's tangent. Okay, so that means theta plus 90 plus phi. I shouldn't call this theta, I should call it alpha. Alpha plus 90 plus phi equal 180. Hey, I did that right. Okay, so alpha plus phi equal 90 degrees. And so theta plus phi equals 90 degrees. And alpha plus phi equal 90 degrees. Alpha is the same as theta. Okay, now I feel you guys believe me. Okay, so let's start trying to fill in this integral now. So I'm going to let that slide for a bit. I have dl cross b, so I have a dl and a b. I need the sine of the angle between them, which we have firmly decided is theta, where this is 0 degrees, this is 180 degrees. What will dl cross b, what direction is that going to be in? And let's do it out here first. So I have dl pointed in the blue, b in the yellow. So what direction will dl cross b? I like this. Into the board. Okay, so we definitely have like a negative z right there. What about over here? What if I have my dl right there? B has not changed direction. Are we still getting into the board? So now my dl is that way. Ooh. My dl is that way. My b is going up. My thumb is going into the board. Okay, awesome. Okay, so I would believe at this point, like all of these cross products are going to be in the same direction. They might not all have the same angle, so they might contribute more or less, but they'll all at least be in the same direction. Okay, so this is the negative z direction. Okay, I'm liking this. This is looking better all the time. Okay, so I'm integrating all my dl's times my magnetic field times the sine of the angle between them. Now the magnitude of dl and the magnitude of my magnetic field are going to be constant. So even though I have to deal with them, they're not going to be doing anything that big. How about the sine of theta? Is that going to be a constant, or is that going to change as I go to different dl's? It's going to change. Okay, so I need to relate my dl and my sine of theta. Or really, I could say I need to relate dl and theta. Sound okay? And we can do that through arc length, because dl is just one small part of this arc, right? So I have my slice here. I've got my arc right there. So there's dl. And dl will be the radius times that small slice of angle, because that is the arc length formula. Is everyone kind of happy with that? If you've probably seen it as like S equals R theta. Okay, so we'll take that and we'll plug that in right there. So our force, now I have I. This magnetic field, is it a constant or a variable? It's a constant, so I'll just move it outside. I have RD theta, sine theta. This is all in the negative z direction. How about that R? Is that a constant or a variable? Constant. So I'm at a point where I'm taking the integral of sine theta d theta. So I'm really just taking the integral of sine. I had IRB sine theta d theta. This is great. What is the sine of theta? I mean, sorry, what is the integral of sine? Negative cosine, correct. IRB, negative cosine. And we hadn't discussed limits yet, so let's talk about some limits. I'm integrating theta. I want to start here and I want to end here. What angle should I begin at and what angle should I end at? Perfect. 0 to 180. Okay, okay. IRB. What is the cosine of 180? Just say it, guys. -1? It's -1. Okay. Sorry, not trying to trick you. -1. Okay, so I have cosine, so I have that minus sign, negative, -1, minus a negative cosine of 0. Can we all agree on 1? Okay, good. And that's all minus z outside. Okay, looking at this, those two minus signs cancel out. Those two minus signs cancel out. And so I really have 1 plus 1, which is 2. We can go over this. I have proven it before. So I have 2 IRB in the negative z direction, and it would really make my day if your eyes lit up and you said, oh my goodness. Oh my goodness, right? It's the same answer. except it's in the opposite direction. So if I asked you for the net force on this thing, I've got plus 2 IRB on the bottom. I've got minus 2 IRB on the top. What is the net force on this loop of wire? It would just be 0. And I'm hoping what you guys see is that when we were looking at this force, what really mattered was how much of this loop was perpendicular to the magnetic field. Where I L cross B, where we cross producted this. So we said only the parts that are perpendicular matter. On the bottom, that was pretty easy because the whole thing was just perpendicular. On the top, we added this dimension of up and down, but that was parallel to the field. That didn't matter. So only the portion of this guy that was perpendicular that mattered. And since we had to go the same way forward as we did get back, because it is a loop, we got the same force one way that we did get the other way. Okay, here's the tricky part, guys. You have correctly told me that the net force acting on this thing is 0. It is an equilibrium. But is it in static equilibrium? Where, for something to be in static equilibrium, not only does the net force have to be equal to 0, but the net torque has to be equal to 0 as well. Meaning that you don't expect it to slide, but you also don't expect it to spin. So this loop that has a force right here out of the page and has a force right there into the page, are you going to expect this thing to spin? I want to hear a yes. And so here's the deal. If I push forward and backwards on this, it's not moving and it's not spinning. But what if I pushed forward over here and backwards over here,
Oh, right.
right? Then it spins. And you notice it didn't like fly out or come back, but it kind of sat in place and spun. And so this loop, while it is in equilibrium, it is not in static equilibrium because we are going to have a torque acting on it, which means it will spin, which I want you to think back, that's what this entire chapter has been about, right? Things aren't moving, they're rotating. And this is what we're going to talk about now in the next 15 minutes is, can we quantify how much torque it will be on a loop of current carrying wire? Which we kind of already did because we did the integral. But now let's do an easier problem. Torque on current loop in a B field. Okay. Okay, so this problem was hard because we had this whole like semicircle thing going. So let's make it, instead of a semicircle, let's just do a rectangle because those are easier. And plus that'll be easy to say, okay, this part of the length is perpendicular and this part is parallel. So we don't need to really like stress over it as much as we did before. We'll put a magnetic field in the same direction. I'll remember that we need a battery in here, where my battery will go like that. I will say that side of my rectangle is A long, and this side of my rectangle is B long. We'll say the current through this guy is A, and pretend like I have something that keeps this from shorting out. Okay, and so what we're going to do is we are going to calculate the force on each side of this. Then we're going to define an axis of rotation. Then we are going to find the torque acting on this. Okay, so 1, 2, 3, 4. Starting on part 1, not plus 1. We have a nice straight line, so we don't need to do the integral. We can just do IL L cross B. And this one's a little bit of a gimme. What's the so on this first just chunk of wire, what is the magnetic force acting on this chunk of wire? It is 0 because my wire is perpendicular to my field on this one. Okay, this one's 0 because my wire is not perpendicular, it's parallel to my field. Okay, let's do the top. Chunk 2. Same current. I have an L, I got a B. Okay, so we're not going to be 0 anymore because now the angle between the wire and the magnetic field is 90. Okay. ILB sine of 90. What direction is this force going to be in? I like it out of the page. So like L, B, out of the page. And instead of L, I'm going to write down B because that's the length of that side. Okay, so I have I, AB in the plus C direction. Okay, everyone good? All right, looking at the third chunk of wire. What's the force on that chunk of wire going to be? Also 0. Good. How about the fourth chunk of wire? Okay, it'll be into the page. Will it have the same magnitude or a different magnitude as the second chunk? Same, right? Because we have the same current, it's the same length, same magnetic field. Only thing that's different is that it's into the board instead of out of the board. Okay, so hopefully you see that you add up these 4 forces, you get 0. So just as it should be, the net force here is 0. But now we need to calculate the net torque, where I don't know if you guys remember, but torque is this rotational force that's R cross F, where R goes from the axis of rotation to where the force applies. Does anybody need to ask a question about torque before we get started? It was like one week, 6 months ago at this point. Okay. Hang with me while we figure this out. Okay, so right now what we have is we have a force coming out of the page up here. So the top part's being pushed out towards you. On the bottom part, that's going into the page, so that's being pulled back. So we expect this thing to spin like this, right? Okay. We can actually make a few different choices for the axis of rotation, but I'll choose one and then I'll choose a different one probably. But for now, let me put it down just the middle, because that makes a pretty easy axis to talk about. That means that the radius for each of these forces goes from the axis down to where the force is applied. Now, in terms of A and B, what are guys, did I screw that up? Yeah, sorry guys. Those two are both B's. Sorry. So that which is good, because in terms of A, what is our radius going to be? Where A is the length of this guy's A. Yeah, so just A over 2. Excellent. Okay. Okay, so that means if I want the net torque, I want the torque on the top plus the torque on the bottom. Do I need to worry? What slide do I need to go back to? Okay. let me know if you need me to go back. I can definitely go back. I'm not doing anything fast today. So are these two forces trying to get this thing to spin in the same direction, or are they both trying to get it to spin in different directions? So by that I mean, if I were trying to get something to spin in different directions, I might apply a force this way while trying to slow it down with my other hand. Same direction. So by pushing forward on the top and back on the bottom, I make it spin more. Does that make sense? So they both have the same direction to them, so I'm not going to worry about a minus sign. They both have the same radius, so I'll have like an A/2 cross the force, which is I little b big B, little e big B. Now I also have a sign of the angle between the force and the radius. So like for the top, the radius goes in the positive y, the force goes in the positive z, the angle between them is going to be 90. Okay. And for the bottom, we actually get the same thing. Same radius, same force. Now my radius points down and my force points into the board. That's still perpendicular to each other. So I'm hoping you see that we have 1/2 AIBB plus 1/2 AIBB. So we really have 1 whole AIBB. Okay, okay. Coming together. Net torque, 1 whole AIBB. Okay, okay. And we notice that we have this nice term A times B. Here's where A is, here's where B is. What is A times B? If I multiplied this side by this side, I get the area. Okay, so I get an area in here. So this is really the current times the magnetic field times the area of my loop. And in fact, we can make some interesting statements that, yeah, we did this for a rectangle, but we can extend this to any shape where we're going to get the area, because we have this idea that really we just care about the perpendicular components. So we can always do this area trick if we want to. Sound okay? So regardless of shape, so like if you have a circle, you do a pi r squared. You can extend it anywhere. Last thing I want to do is I want to put a direction on this torque, because torques do have directions. And I don't know if you guys remember how directions work when you spin. So this thing's spinning like this, right? And this, I don't know if you noticed, this is kind of hard to convey, especially with my camera marrying me on top of that. So instead of saying, hey, we're rotating clockwise or counterclockwise or anything, we'll use a right-hand rule, where we take our right hand, we line it up with our picture, and we curl our fingers in the way we expect this thing to spin. And we point our thumbs, and I see everyone's thumb is pointing to the right, whoosh, to the right, which for us, that means the positive x direction. And so we say the torque in this case is going to be in the positive x direction. Does that make sense? Okay. I am honestly pretty close to the end of this chapter. I am going to extend. I think I just want to finish, like do a torque problem or something next time to make sure we get it. And talk a little bit about magnetic moments. So I'm going to extend this chapter to next Tuesday for the expert TA. You do have the quiz over the weekend. That's not going to change, but the homework I won't have due until till Tuesday. Although I think you know everything you need to know to get it done now. Okay, any questions, online people? Okay, have a great weekend. Don't forget to turn in your projects. Lab people, I'll see you in 15 minutes.